If you've ever taken a dive in the ocean or, accidentally swallowed a massive gulp of seawater at the beach, you know exactly what it tastes like. It is incredibly salty. But have you ever stopped to wonder who or what actually added all that salt to the ocean in the first place? It's this staggering planetary puzzle. And today in this explainer, we're going to explore exactly where it all came from. Spoiler alert, it has a lot to do with something as simple as a raindrop hitting a rock. Let's get right into it.
So, when we break down the actual composition of ocean water, we find it's about 96.5% pure water and only about 3.5% salt. Now, at first glance, 3.5% might not sound like a whole lot, right? But we really have to put this into perspective. Our oceans cover roughly 70% of Earth's entire surface, and they account for a staggering 97% of all the water on our planet. So when you take 3.5% of practically all the water on Earth, well, that seemingly tiny slice actually represents a massive, literally incomprehensible amount of salt.
Okay, let's really dive into this. To understand just how much salt that 3.5% represents, imagine a single giant cube of ocean water, 1 mile wide, 1 mile long, and 1 mile deep. The amount of salt suspended in just that 1 cubic block is a mind-boggling 220 million tons. 220 million tons. And that's just in 1 cubic mile. It's absolutely wild. So the totally vital question we have to ask ourselves here is, where in the world did all of this come from?
To solve our salty mystery, we have to investigate two prime suspects. The salt in the ocean mainly comes from two primary sources: runoff from the land and openings way down in the seafloor. It's kind of like a massive planetary detective story, and the evidence points both up to the surface and deep, deep underground. We're going to explore both, but let's begin our investigation by looking up at the sky because this is where the real magic happens.
The journey begins high in the atmosphere, and it involves a completely fascinating chemical transformation. This is absolutely crucial to understand. As rain forms and falls through the air, it actively pulls carbon dioxide directly out of the atmosphere. This addition of CO2 creates a slight acidic shift in that fresh rainwater. Now, it's a tiny chemical change, but it triggers massive geological consequences. When these slightly acidic drops finally strike the Earth, they basically act as a planetary mining operation. The water slowly eats away at the solid rocks it flows over, actively extracting and carrying off tiny amounts of salt and other dissolved minerals that were locked inside those rocks for millennia. Just think about that for a second. Every single time it rains, millions of gallons of slightly acidic water are out there, relentlessly eroding rocks and mining salt right out of the earth.
But here is the really surprising twist in our story. Even after falling through the atmosphere, turning slightly acidic, eroding all those rocks, and picking up those dissolved minerals, the runoff water is still basically fresh. Seriously, yes, there are absolutely traces of salt in it now, but it's totally negligible. It's not nearly enough to make the water undrinkable for us. So, if this mineral-rich runoff flowing across the land is still fresh, how does it suddenly become that 220 million ton saltwater mixture we see in the ocean?
Well, when this slightly mineralized rainwater finally reaches the ocean, it hits what is essentially a massive biological filter. Marine organisms eagerly extract dissolved minerals, like calcium, that the runoff brought in. They use it for their own biological processes, like building their shells and skeletons. The salts, however, that gets left behind. Marine life just doesn't consume it in the same way. So over millions and millions of years, as the calcium is constantly being used up by ocean life and the salt is just left alone, it continually accumulates. And that slow, relentless buildup is exactly what turns the ocean water intensely salty and undrinkable.
Okay, so that's the rain and runoff part of the puzzle. But our second suspect takes us miles beneath the surface to explore hydrothermal fluids. Down in the absolute deepest parts of the sea, the ocean floor isn't just a solid, unbroken bowl. It's actually heavily fractured with cracks. And when the already salted ocean water seeps down into these deep, dark fissures, it meets rocks that are intensely heated by magma radiating straight up from the Earth's core. Down in these deep Earth cracks, that intense magma heat triggers an incredible chemical exchange program. It's a real game changer for the ocean's chemistry. As the seawater interacts with the superheated rocks, it actually loses elements like oxygen, magnesium, and sulfates. But in return, the water actively strips heavy metals like iron, zinc, and copper right out of the surrounding rock. This chemically altered, superheated water is then shot back out through vents in the seafloor, carrying all these additional metals and minerals with it. So, as a direct result of this intense, deep Earth chemistry, the ocean water gets even saltier.
Now I know exactly what you might be thinking at this point. We've established that rain is constantly eroding rocks and carrying traces of salt all across the land, right? Which brings us to this massive paradox. If that erosion is happening literally everywhere, why don't our rushing rivers and huge lakes taste like the beach?
It's a great question, and the answer lies entirely in momentum. Oceans act as giant, inescapable basins. Once water and minerals arrive there, the water can evaporate up into the clouds, but the salt, it has nowhere to go, so it just sits there, having millions of years to accumulate. Rivers and lakes, however, are constantly in motion. They actually do contain those tiny traces of eroded salt we talked about, but they act as rapid delivery systems. Because they're continually flowing, it's incredibly hard for that salt to ever accumulate in one spot. Before the salt levels can ever build up, the flowing river simply washes it straight into the ocean's massive accumulating basin.
Before we wrap this up, what exactly is this 220 million ton mixture actually made of? We've talked a lot about salt and minerals generally, but it turns out that 85% of all the dissolved minerals in the ocean are just two elements, chloride and sodium. Yep, good old sodium chloride, table salt, makes up the vast majority of it. That leaves just 15% for literally everything else that was stripped from the rocks by the rain or vented from the deep sea. So, we've tracked the fascinating journey of a slightly acidic raindrop eroding solid rocks all the way down to magma-heated vents cracking the seafloor. It's this brilliant, beautifully complex system that's taken millions of years to build, providing a home to countless aquatic animals and plants. It plays a massive role in the very existence of our Earth. So, knowing just how delicate and interconnected this massive system is, how can we ensure we keep our oceans clean and free from pollution? Because ultimately, it's our responsibility to protect this incredible salty environment. Thanks so much for joining me for this explainer, and I'll see you next time.